Hi everybody, this is one last quick video where we will look at the thermodynamic parameters that go into calculating the mantle potential temperature T sub P that's shown over here in column Z and AA in the sheet Calc P iterative. If you're interested in inputting P, everything is done exactly the same way. We have two columns that represent two different estimates, as we'll go over, and the same kinds of thermodynamic calculations over here, AC through AH. And then over here, columns, also AC through AH. So we'll just use Calc P iterative as an example. So first, let's take a look at this equation here for mantle potential temperature. What it does is it takes care of two corrections. If we come back over here, there's the correction along this adiabat. So let's take a look at first at this correction for a solid adiabat. That's this very steep line, dt dp is equal to T alpha V over Cp. That's temperature multiplied by the expansion coefficient of thermal expansion. And then that should really be a bar V, the molar volume, or the volume of 1 mole of mantle material. And then that product, T alpha V, is divided by Cp, the heat capacity. That is shown over here. So here's the mantle adiabat. You can put in a constant value. So I think in Mackenzie and Bickel, they have 1.2 degrees centigrade per kilobar. We're entering the values in centigrade per GPa, so that would be equal to 12 degrees centigrade per GPa. If you just want to use a constant value like that, then you could just put a value there, and this value will be updated. There is another correction, not only for the mantle adiabat, but then as solid mantle rises, it'll eventually hit the mantle solidus, and when it does, it'll begin melting. And some of that energy that goes into converting solid into liquid will force the temperature of the entire system to decline as we're converting that energy. And so when we take a volcanic rock as a signal of mantle potential temperature and we estimate the temperature of that liquid, that is not the temperature that we want to project up to the surface. We want to first correct for the heat of fusion to come back to the case of a parcel of mantle where no melting has taken place. It's the solid mantle, its projection up to the surface, that gives us a true mantle potential temperature. Some people forget that step, and when they do so, they're taking this liquid, projecting it up to the surface, and they get a temperature that is not strictly in accordance with the idea of a mantle potential temperature as defined by Mackenzie and Bickel. You want to have something that is really independent of the amount of melting. And that's why they chose the case of a parcel of mantle that's unmelted to project to the surface. Well, how do we make this upward temperature correction? Cawthorne gave us the equation back in 1975, well before the Mackenzie and Bickel paper. The delta T is equal to F, the melt fraction, multiplied by the heat of fusion divided by heat capacity. And those values are given over here. So notice that the V and alpha, these things are constant. I just use a V. I think the nominal value, the default value is 5.07 in the spreadsheet that you download. But if you don't like that in terms of the volume of a parcel of mantle, you can put in 6 or something like that. And I'll update this value here. If you like an alpha of, let's say, 3.3, which I think is the default in the sheet that you'll download it, again, this mantle adiabat, that variable case will be calculated over here. And then it's this mantle potential temperature in column AA that will take account of that variable mantle adiabat. So you can look at this adiabat here, this mantle potential temperature here, which uses a constant adiabat, or this mantle potential temperature over here, which uses the variable where you can actually adjust the values V, alpha, and Cp. Cp is over here. I don't have it as a separate line item. I'm letting it vary as a function of temperature and pressure. Well, actually just as temperature here. And so that goes into the variable case over there. And then that upward temperature increase for the heat of fusion. In another video, we talk about how this calculation is connected to the value of F. This value is being calculated from some equations over here. If you don't like those equations, you can enter a different equation or just put in a constant value for the amount of melting. Or if you just want to look at the heat of fusion or the heat capacity, if you want to change these values, if you, let's say, you think that the heat of fusion should be 120 kilojoules per mole, you can enter that here. If you think the heat capacity should just be a constant 200 joules per mole dot K, you can enter that here, and you'll get an update value for that ratio, delta H over Cp, and that'll affect the temperature increase. And then, for again, if you come over to this column in Z, this is going to use a constant value. So this variable case over here, where we let H and Cp vary, that's going to play into this estimate for Tp. But what if you don't want to fuss with any of those? Over here, we just have a constant value, 674.3. That is for the value of delta H over Cp. So let's say you don't want to estimate these individually and you think the value should really be 500. This isn't really linked to an external cell, but you can just come over here and change this to, let's say, 500 or 700 or whatever you think it should be. Although I would recommend not going too far away from the calculated values here. But you can enter those values. We'll just go back to the default 674.3 if you just want to keep it constant. So you can change these values, V, alpha, heat capacity, and the heat of fusion. That'll play into these mantle potential temperature estimates here, or you can use the constant values and they'll play into these values over here. All that stuff is variable. So I hope a little bit of that is helpful.